What questions do you have? So I think I sent an email, but if I didn't, homework on 4.1 on web assignment is due tomorrow. 4.2 is due on Sunday. Listen to what I said, yes? Yeah, okay, cool. I went in and said it, so hopefully that's right. Anyway, again, I'll be gone and leaving first thing in the morning. But if you email me, I'm still available through email. So I can definitely chat. My talk's not till Sunday, so I can definitely chat. Got questions. So Saturday, try again. Coming back Saturday night. So be home on Sunday. Anyway, you don't care. It's fine. No questions? Things are going okay? All right. We're going to do another example with vector space stuff and then move on to subspaces today. We'll start subspaces today, which are basically just subsets of vector spaces that are also vector spaces. We'll start that today. That'll be the last new section that we'll have for the exam next week. We may cover new material past that, but section 4.3 will be the last one that's actually on the exam for next week. Okay. All right. So let's do an example here of the following. Let's say we let V be two-dimensional vectors again, so vectors in R2, but let's define x1, y1 plus x2, y2 as normal addition in the first component, but the second component we'll add a 1. We'll add them together, but also add a 1. Okay, so that's what our addition is going to be defined as. And we'll define scalar multiplication for any vector xy. It'll be normal in the first component, but in the second component, we'll add, well, not only, the second component's of y. We'll multiply the c times y, c times the y, but we'll add c and subtract 1. I'm going to tell you now that this really is a vector space. It actually satisfies all 10 axioms. Okay? I'm not going to go through all 10 axioms because, as you know, those take a while, right? But let's go through some interesting ones. One interesting, I think, well, obviously it's closed, right? If I add 2 vectors from R2, I get a vector from R2. In R2, sorry. Right? If I take 2 vectors in R2, I get a vector in R2. So clearly it satisfies the first axiom. If I take a scalar times a vector in R2, I get a vector in R2. So it clearly satisfies the sixth axiom. You agree with that? We don't have a problem with closure because, again, here everything is real, right? The c is real, the x's are real, the y's are real. So everything's taking place in the real numbers, and I'm putting 2 components on it, so it's in R2. So closure is not an issue. I think commutativity of addition is pretty straightforward as well. If I add x1, y1 to x2, y2, I get that. If I add x2, y2, and x1, y1 in the other order, all it's going to do is just flip these 2 around and those 2 around. But addition is commutative, so it doesn't matter, because that's a real number addition again. So commutativity makes sense, right? So I think those 3 we don't have to do a lot of work for. I'm not going to do these in order because there's some that are easier than others. So let's try to take care of some of the easy ones. Let's take care of the last one. That one's pretty straightforward. If I do the 10th one, I'm not doing them in order because I want to get to the more interesting ones at the end. If I do the last one, if I do 1 times xy, what do we get? So I get 1x right here. This one, if I write it out long ways, what do I get in the second component? yeah, 1y plus 1 minus 1, right? And we really do get xy, which is what we're supposed to get, correct? Better get that, right? All right. All right, so let's see about some of these other ones. Let's do associativity of addition. I think that's the third axiom, right? So I have a grouping where I've grouped the second two together. I also have a grouping where we grab group the first two together. But again, when we've got it grouped like this, we're going to add the second two together first, right? When we add those together again, we're just adding the first components just like we always do. The second components, we get a plus 1 on the end, right? What do we get when we add again now? So we exclude x3 in that first component, right? So you get y1 plus y2 plus y3 plus a 1, and then what goes on the end? Another plus 1, right? So remember the way it's defined, we define regular old addition in the first component, but in the second component, you add the two and then stick an extra plus 1 on the end, right? We agree? Okay. If we do the other way around, what do we end up with? Which two do we add together first? Okay, so what do we get when we add those two together? Good, y1 plus y2 plus 1. Again, every time we add two vectors together, we're tacking on an extra plus 1 on the end. Right? Now what do we get when we add these two together? Okay, I get the x1 plus x2 plus the x3. What do we get in the second component? Yeah, plus an extra 1 on the end. Good. So again, in the second component, we add the two second components and then stick an extra plus 1 on the end. Right? Are these two things the same? I think they are, aren't they? Yeah, remember, we had real number addition in here, correct? So we can rearrange groupings and we can rearrange the sums. Right? So I could regroup. Well, I can actually just delete the parentheses. If it's associative, we don't even need to bother writing the parentheses, right? Get rid of the parentheses and I can move the plus 1s around. So those two things really are equal to each other. So we really do get associativity here. We agree? Okay. All right. That one was a little bit more complicated, but not too bad if you just go through what the rule says, right? Just making sure that every time you add the two second components together, you stick an extra +1 on the end. That's what the rule says. All right, so let's do a trickier one. The fourth one says we need a zero vector. Now, I've mentioned this several times before, and we've done other examples. The zero vector does not have to be what you're used to the zero vector being, right? Remember, for the zero vector, I need x, y plus something, right? Or if this is my zero vector here, whatever I call it, if it's a, b, what does it have to equal? It has to be the x, y again, right? That's what we need, isn't it? What does the left-hand side look like if I actually call it a comma b? What does the left-hand side look like? Okay. Let's leave +1 again, right? We agree? Okay. And this is still has to be equal to xy, doesn't it? Now, looking at these two vectors, if they're going to be equal, what does your a have to be? 0. Yep. I better have a be 0, but what does the b need to be? It better be -1, right? Because I got to cancel out that +1, don't we? Right. So your zero vector in this case is the vector 0, -1. Which is a little strange. The reason why we need that -1 in there, though, is to cancel off the +1 that we decided to add in there. Again, the whole point of your zero vector is that when I add it to any vector, I end up with that vector, right? And then what we started with. Now, we could go through and check that it really does work, but we made it work, right? Not a lot of checking to do here. All right, we set this up to solve this equation and figured out what these had to be. Does that make sense? Okay. Now again, we've set this up so that this zero vector works for every single vector in V. It works for every single vector in R2 under this addition. It's the same zero vector that works for every single vector, right? It can't depend on what the vector is, right? It has to be one vector that works for everything. Now, for inverses, you get to choose what the inverse is, right? Each vector has an inverse that goes with it. But if you change the vector, it changes the inverse. Okay? So in 5, when we're finding inverses, it'll be in terms of your vector, right? So if I start with an xy, and I want to add something that is its inverse, if this is your v and this is -v, what are we trying to get back to when we're doing inverses? The zero vector, right? In this case, what is your zero vector? 0, -1. We need to get back to this zero vector, right? We have another equation to solve again, but don't use 0, 0 here, because that's not what the zero vector is, right? The zero vector here is 0, -1. This is what we're trying to get to. But it's the same kind of idea. Now simplify your left-hand side. Again, we get x plus a, y plus b plus 1. So now, again, we should be able to pick what your a is and what your b is. What is a? -x. And what is b? Is -y minus a 2, right? Because I have to get to -1. I need the -y to cancel out the y. I need the -2 to get all the way down to -1, right? So if we write it, the opposite or the additive inverse of xy in this case is -x, but it's -y minus 2. that make sense? Is it okay? All right. So notice that we've gone through, we've seen that it satisfies the first 5 axioms now. We talked about 1 and 2, right? But we showed 3, 4, and 5. 6 we also talked about. We already showed 10 works, so we've got 7, 8, and 9 to worry about. I'm not going to go through all of them. I'll leave a couple for you for practice. But let's say we have the constant times a vector sum. And then does it distribute over addition? Again, what do we do first? In the first line, what do we do first here? We add the 2 vectors together, right? When we add those 2 vectors together, what do you get? Okay. Yeah, the x1 plus x2, y1 plus y2 plus 1, right? In the second case, what do we get? So when we multiply here, and so remember the scalar multiplication is just multiply the c times the first component. What do we get in the second component? Plus c minus 1, right? We agree? Yep. Okay. Let's see if it works the other way. I'm guessing it's good. I'm guessing of the. Let's put it this way: of the 2 components, which one are you worried about? The first one or the second one? The second one. It's the weird one, right? All right. So when we do this one now, multiply the c times the x1, y1. What do you get? Okay. And in the second one, we get the same thing, just with 2's rather than 1's. We agree? When we add, now, we still add just the first 2 components together. What do you get in the second component? You don't have to simplify it. You can just tell me how you would do it. Okay. Yeah, so we have the cy1 plus c minus 1 plus cy2 plus c minus 1. And then what goes on the end? Plus 1, right? The rule says add the components and then add an extra 1 on the end, right? Add the 2 components together and then add a 1. Do these 2 things equal to each other? Well, I've got cy1 in both of them. I've got cy2 in both of them. I've got a plus c and a plus c. So I got 2 c's, right? And then the constants work too, because I got a minus 1 plus 1 equals a minus 1. So we really do get that those 2 things are equal to each other. The algebra here is not hard. It's just keeping track of what the rule says to do, right? We're not doing hard algebra at all. Save that for later. I'm not doing hard algebra for all. We just change what the rule says. So this just shows you how the distributivity for scalar multiplication works over vector sums. You would need to do the same thing for scalar multiplication over a scalar sum, right? The other one is for 8. You would have C plus D times XY, and you would have C times XY plus D times XY. Now notice in this case, when you do this one, you don't get the extra plus 1, right? Because all we're doing is this scalar times that, right? You get the extra plus 1s here when you'll add these two things together. So see if you can run through that for practice and see if you can get through showing that those two things really are the same thing. Okay? I'll leave that for you for practice. It should behave similar to what we just did for 7. Even though it looks weird, I know it looks weird. Okay? But just if you follow what the rules say to do for the addition and the scalar multiplication, you'll get the same thing on both sides. I promise. And then you should also do 9 as well. 9 is your associativity property, right? But I'll leave those a couple for practice so that you can go through those, see how they work. On your exam, I'm most likely not going to make you go through all 10 axioms to show that something is a vector space because that takes a lot of time, right? You need to know what the axioms are and how to verify them. And I'm probably going to say this is a vector space. Verify this particular axiom, or this is a vector space. What is the zero vector? What is an additive inverse of a vector? Those kind of things. So that you're not having to try to go through all 10 things. That makes sense? Just being able to verify. I need to make sure that you can verify some of them, but going through them all over and over and over again is particularly interesting and eager. That's okay? All right. So let's move on where we start to get things back to normal, if you will. Okay? Again, the reason why we do this is from an abstract perspective and play with these weird things. The whole idea of it is to say vectors can be anything as long as they satisfy the properties that we want to do. Okay? The vectors don't have to be components in R2. Now, usually when we move and start doing things that are vectors that aren't traditional vectors, usually we're thinking of things like functions. Maybe polynomial functions, maybe continuous functions, maybe differentiable functions. But usually we're thinking about functions also being vectors. But you don't want to have to go back through and prove theorems about specific to vectors that have components, and then move to things that act like vectors but they're functions, or things that act like vectors but they're matrices. Okay? That's why we do this from an abstract perspective and play with things a little bit, just to try to emphasize, that chair should not be there, just to try to emphasize that vectors don't have to be what you're used to calling vectors. They can be other things as well. Well, we'll move over, like I said, to things that are a little bit more interesting, or a little bit more, not interesting, a little bit more what you're used to dealing with, and then start talking about subspaces of things. So section 4.3 talks about subspaces. And as a definition, if we let V be a vector space, as soon as I say that statement, by the way, V automatically has a whole bunch of structure, right? As soon as I say that I have a set that is a vector space, first off, I know it's not empty. We don't have empty vector spaces. There has to be stuff in it, okay? But there's an addition that is defined. There is a scalar multiplication that is defined, and it satisfies all 10 of those axioms. Those two operations satisfy all 10. So as soon as you say these words, vector space, you get a whole boatload of structure. Okay? All right. When we're talking about subspaces, we start talking about subsets. That's our subset symbol. If you're not familiar with it, it just looks like an elongated C with an equal sign. It's supposed to make you think of less than or equal to. So W is a subset of V, so it just means it's a piece of V, maybe all of V. It also has to be non-empty. You know that from discrete math, when you've had discrete math, from discrete math, the empty set is a subset of everything. So technically, when I write that, W could be empty, but when we're talking about things that are vector spaces, they can't be empty. All right. We say that W is a subspace of V if W is also a vector space under the exact same addition and scalar multiplication of V. We're not changing anything. We're just putting blinders on. We're shrinking down where we're looking. That's all this says. We're not changing the addition. We're not changing the scalar multiplication. We're just saying, we're just shrinking down what we're looking at. Okay? So let me give you a specific example. A relatively easy example. Let's say V is R2. W is the set of all x comma 0. The first component can be anything, but the second component has to be 0. Okay? W is also a vector space using the exact same addition and scalar multiplication. By the way, if all I do is write V as R2, assume that your addition and scalar multiplication are as usual. Adding the two components together like you would, taking the scalar and running it through the two components like you would. Okay? Unless I tell you addition or scalar multiplication is weird, assume it's not weird. Okay? Fair enough? All right. So over here, we know V is already a vector space. So again, it comes with lots of structure. We know that the addition is commutative. We know the addition is associative. We know that scalars distribute over vector sums. We know that the scalar multiplication distributes over scalar sums. All of those things, right? Those work for all vectors in W or in V. Well, if they're going to work for all vectors in V, they're going to work for W, no matter what, right? So the only things that you have to worry about when you're looking at if something is a vector, a subspace or not, is it closed under the operation? And does the 0 vector and inverses lie in there? Those are the only things that are weird, right? It's the only thing you have to worry about. Everything else says they have to work for all vectors in V. If they work for all vectors in V, they certainly work for all of the vectors in W, right? So let's just look at this particular set. If I take two vectors out of W, specifically out of W, and add them together, do we land back in W again? Yeah. Sure does, right? The reason why is because we're using 0 for that second component, correct? Okay. If I do a scalar times a vector from W, do I land back in W again? Yeah, sure do, right? Because again, I'm using 0 for that second component. So this is definitely closed under addition. It's definitely closed under scalar multiplication. This as a set, right? Without a doubt. Okay. The other things that I said to have to worry about is there a 0 vector? In particular, in your set V, what would be your 0 vector? 0, 0. Does that lie in W by the definition? Is 0, 0 in W? Sure is, right? So it's going to have a 0 vector. How about additive inverses? What is the additive inverse of a vector in R2? This is the negative of each component. Is that going to work for vectors in W? Does the negative of a vector lie back in there again? Yeah. So this really is going to be a subspace in this case. Now, one of the things that we know, by the way, is that some things that we already proved for all vector spaces. If I do 0 times a vector, what vector do we get out? If you do the number 0 times any vector, you get what vector back out again? 0 vector, right? Correct? If I do -1 times a vector, what vector do I get? The inverse, the additive inverse, right? So what it turns out to be is a theorem. Oops. If V is a vector space, and if W is a subset of V, non-empty again, then W is a subspace of V if and only if W is closed under addition and scalar multiplication. And again, this is the same addition and scalar multiplication of V. So proving something is a subspace is a lot easier. When you want to show that something is a subspace, you only have to show two things. It's closed under addition, it's closed under scalar multiplication. And the reason why we only have to show the two is because, remember, there are 10 vector space axioms, but the axioms 2, 3, 7, 8, 9, and 10 are all work for all vectors from V, right? And all scalars that you can pick. Doesn't say anything about having to be from W or not, does it? 2 is commutativity, 3 is associativity, 7 is distributivity, 8 is distributivity, 9 is associativity, 10 is that scale, right? 1 times a vector is a vector, right? Those 6 you get for free if it's a vector space, right? If it works for everything in V, it works for everything in W, because W is just a piece of it, okay? We also get 4 and 5 if it's closed, because if it's closed under scalar multiplication, then 0 times the vector is 0 vector. If it's closed under scalar multiplication, we know that 0 times that vector has to be back in W again, which means the 0 vector has to be in W. So I don't need to check 4, right? If it's closed under scalar multiplication, I don't have to check 4. If it's closed under scalar multiplication, I know that -1 times the vector is its additive inverse, which means the additive inverse has to be back in there again. So I get 5 for free. It's closed. So you only have to check 1 and 6 for subspace. That cuts down a lot of work, right? So to that end, let's see if we can do some practice problems here and verify that some things are, or whether or not something is a subspace. There we go. All right. As I go along with some of these practice problems here, we're going to get some notation along as well. So number 1 here, your vector space, it says, is the set of all 2 by 2 matrices. I think we've used this notation before. Your first subscript refers to number of rows. Second subscript refers to number of columns. So when I write M sub 2, 2, I mean the set of 2 by 2 matrices. And again, if I do not tell you addition and scalar multiplication is weird, assume it's normal, okay? So in this vector space, you're going to add matrices like you always do. and do scalar multiplication of matrices that you always do. And we've already proven things way back at the beginning of the semester that says that all the vector space axiom things are true, because we know that matrix addition is commutative, and matrix scalar multiplication of matrices distributes over sums and all that stuff. We did all that stuff earlier this semester. You loved those proofs, right? When you got to get down to the general entries. But those were fantastic. I know you all loved those. All right. So that's our vector space. W here is a set of all matrices D, such that D is diagonal. What does diagonal mean again? If it's a diagonal matrix, what does it mean? If I have a letter here and a letter here, what are the other ones? Zeros, right? The only non-zero entries can appear down the diagonal, right? That's what that looks like from W. Now, A or B or both could be zero. The definition of diagonal just says that if you're not on the main diagonal, then you are a zero. Okay? It does not say that if you are on the diagonal, you're not zero. Okay? Just like triangular, when we talk about upper or lower triangular just said if you're below the main diagonal, you're zero, but you might have zeros other places. Okay? So by definition, the zero matrix is diagonal. It's also upper triangular. It's also lower triangular. All right. So to determine whether or not W is a subspace, we need to show that it's closed under addition and closed under scalar multiplication. Those are the two things we have to show. Okay. So let's let A00B and C00D be elements of W. And literally just add them together. What do you get when you add those two matrices together? Good. Is this a diagonal matrix? Yeah. So this is back in W again, right? So W is closed under addition. Oh, let's not use C. Let's use K. Since I already used C for a different letter. Let's do scalar multiplication. If I do the scalar times the matrix, what do you end up with? Yeah, 0 Ka0, 0 Kb. Is that diagonal? Yeah. So this is back in W again. So W is closed under scalar multiplication. We've shown that it's closed under addition. We've shown that it's closed under scalar multiplication. Since V is a vector space, we get all the other ones for free. We're done. That's it. That's all we have to do. So this tells us that W is a subspace. Nicer than checking 10, isn't it? Okay. We're going to do more, but questions on this one? All right. Let's look at 2, where it says V is the set of all continuous functions on the interval AB. The notation for that is we use a capital C for continuous, and then the interval notation AB here to say that it's continuous on that interval. If we start putting superscripts on here, like a 1 or a 2, If you put a 1 on here, that's the set of functions that are once differentiable on AB. If you put a 2, that's the set of all functions that's twice differentiable. If you put an infinity on here, it's functions that are infinitely differentiable on AB. So to give an example of something that's infinitely differentiable, polynomials are infinitely differentiable because eventually you get to 0. Sine is infinitely differentiable, cosine is, e to the x is, all those things. Okay. Anyway, that's what the notation means. The reason why we want continuous functions is because we want to make sure the Riemann integral exists. If a function is continuous, then we know we're guaranteed that the integral exists. So we're looking at the set of all functions that have integral 0 over the interval. Okay? And this is where I said now we're starting to treat functions like they're vectors, right? The previous one we treated matrices like they're vectors. Here we're treating functions like they're vectors. Okay. Again, same idea though. Let's just let f and g be in W. If it's going to be closed under addition, I need to show that f plus g is back in W again. What is the defining characteristic for being in W? If you're a function in W, what has to happen? The integral has to be 0, right? So if f plus g is going to be back in W, I need to show that when I integrate f plus g over the interval from A to B, I get 0. Now remember, I know that f and g already are, right? I get to assume that, correct? The closure says that if I start with 2 things in there, then the sum of the 2 things is back in there again, right? That's an important part. If the 2 things are in there, okay? All right. So again, to show that f plus g is in W, we need to say something about the integral of f plus g, right? But what do you know about integrals and sums? How do integrals behave with respect to sums? You can split it up. Good, yep. And this is why I was just making a big deal about knowing that f and g are in W, right? Since f is in W, what is that first integral equal to? 0. Since g is in W, what's that second integral equal to? 0. And 0 plus 0, still 0. Good news is that if the thing you're calling 0 is supposed to be 0, that fact never changes. Doesn't matter what structure you're in, if the 0 means what it's supposed to mean, then that fact never changes. That 0 plus 0 is 0. Other facts might change. It's possible to find a structure in which 1 times 1 is 2. But if a 0 means what 0 is supposed to mean, then 0 plus 0 is 0. Okay. That's a good thing, right? At least you know that's one constant in life. Okay. All right. So what does this tell me? I showed that the integral of this thing is 0, so where does this thing live? W, yeah. Now let's take a scalar. I need to show that the scalar times any function from W is back in W. You just told me the defining characteristic of being in W is that it integrates to 0, right? So do the same thing. What can I do with the scalar with respect to the integral? Take it out, yep. And then again, where does f live? In W, so that integral is going to be 0. And if I take that constant times 0, we get 0, yeah. So where does it say C times f lives? In W. So we showed that it's closed under addition. So it's closed under addition, closed under scalar multiplication. So what does that say about W? It's a subspace, yeah. These are probably better than those abstract vector space proofs, aren't they? They make a little bit more sense, don't they? I agree. They make a little bit more sense. All right, let's look at the third one here. V is the set of all functions over the real line. All that means is that no matter what you plug in, you get an output. So it just means the domain is all real numbers for the function. The notation for that is just a capital F. Anytime you specify an interval here, it's talking about the domain. So this is just a set of all functions that have domain negative infinity to infinity. Just introducing you to some of the notation that we have as we go along here. Okay. All right. W is a set of all functions f such that f of 0 is 1. Now notice in the previous example, the reason why the previous example worked was because when we split the integral up, I had 0 for both pieces, and 0 plus 0 was 0, right? Okay. What's going to happen here? If I let f and g be in w, if f plus g is going to be back in w again, what's the defining characteristic for being in w? What has to happen? What does it say? When we plug in 0, we get out 1, right? That is the defining characteristic for being in w. Is the functions for when you put in 0, you get out 1, right? So if I try to put in 0 into the sum, because again, I'm trying to show that the sum is back in w, right? The defining characteristic for being in w is that when you put in 0, you get out 1. So I'm putting in 0 and seeing what I get out. Okay? Now, much like what we did for the integral, well, how is f plus g of 0 defined? It's f of 0 plus g of 0, right? But what is f of 0 plus g of 0 in this case? F of 0 equals 1. G of 0 is 1. 1 plus 1 is 2, right? Is that 0? No, not today. Ask me if you're taking abstract algebra in the fall. 1 plus 1 might be 0.
1 plus 1 could be 2.
But here, 1 plus 1 is 2. We're all good with that. It's not 0. So what does that say? Are we closed? No. So f plus g is not in w. And we're done. W is not a subspace of E. We don't need to check scalar multiplication. Right? In order to be a subspace, it has to be closed under both operations. If you show that it's not closed under one of them, you're done. That's it. Okay. Now, one thing you might notice here is that, remember, in order to be a vector space, you have to have a 0 vector, right? In the set of all functions, what is your 0 vector? What do you add to any function and not change the function? The 0 function, right? The f of x equals 0 would be your 0 vector, right? Is the 0 vector even in this set? No. It didn't have a hope of being a subspace, right? Remember, the 0 vector for the vector space has to be in the subspace if it's going to be a subspace. That's because of the closure property again, right? If I take the number 0 and multiply it by any vector, I get the 0 vector, right? So if it is a subspace, by closure, the 0 vector from V has to be in W. The 0 vector in V here is not in W, right? So it couldn't have been a subspace to start with. And that would have been a perfectly good explanation as well. So anyway, we got more practice problems there. We'll talk about some more subspace stuff on Monday. But you should try to practice those problems and see if you can show whether or not they're subspaces. Okay? All right. Have a good one. Now remember, no class Friday because I won't be here. But again, you can email me if you've got questions.
Do a class tomorrow morning.
No.
Okay.
No, I'm leaving today. So, yeah. Numerical's not happening tomorrow either.
I'll see you next Thursday.
Yeah.